So today I'm going to present our work, MS-PTP, protecting network timing from Byzantine attacks. So I am Shanghao, the first author of this paper. So to begin with, let me provide some motivation and background for this work. So the question is why time synchronization is so important in the different networks. So currently, many time-sensitive applications, they actually impose very stringent time synchronization requirements. And the failure to meet these requirements can cause significant consequences. For example, the 5G URLLC actually requires a 1.5 microseconds level synchronization across its nodes. And the IEEE TSN standard requires its clocks to be synchronized within 1 microsecond. And for high-performance computer clusters, it is estimated that milliseconds level desynchronization across nodes can cause significant performance degradation. And for the sensors in the autonomous driving, the desynchronization of them can even cause safety hazards to humans. So currently, there are three well-received time synchronization mechanisms, including the very famous NTP, the PTP, and the GPS-based method. So the GPS-based method actually achieves the best accuracy among these three mechanisms. However, it requires for the GPS antenna and is most used in outdoor scenarios. And for the NTP, you can get access to the NTP service anywhere in the internet. However, the accuracy of the NTP is relatively low in the scale of milliseconds. For this work, we are focusing on the PTP, which actually provide an accuracy in the level of 10 microseconds, and it do not require some external hardware devices such as the GPS antenna, and can be used in the local area networks. So before I introduce our attack and defense, let me first provide a technical overview of the PTP. So PTP is currently widely used as the de facto solutions to highly accurate clock synchronization. So it guarantees a sub-microsecond level accuracy, and it has higher accuracy than NTP and better flexibility than GPS, as we have mentioned. And the PTP actually established a tree-structured master-slave architecture before it goes on the actual timing transfer session. So as we can see here in the left figure here, the time server in the network transfers the information from itself to its client through this architecture. So PTP, as we have mentioned, has been adopted by many industrial standards as the solution to provide time synchronization service, such as the TSN, IEEE smart grid, the telecom, and automotive standard. So as a first step, PTP established an architecture in the network. So to finish this, it specifies a dynamic leader election procedure. So the nodes, when they first join the network, they will broadcast and announce messages that contains the clock quality and the identity of its sender. So all of the nodes in the network, they will compete with each other by comparing their clock quality with the announced messages they have received, and only the best one, the most accurate clock wins this election process, and it will serve as the ground master node of the network. We can see this procedure in the left figure here. So the ground master node actually wins this election procedure because it is the best one. And after this dynamic leader election procedure, it is the only remaining node that is still broadcasting this announced message. So after the establishment of the network architecture, the PTP utilizes a two-way time transfer method to transfer the timing information from the master node or the ground master node to their clients, to the slave node. So during this process, we can see from the figure here, the master node first send a sync message, and the slave node send back a delay request, and the delay response is sent back to the slave node, and multiple measurements, including the T1, T2, and the CF1, CF2 we have drawn here are measured. So the client can measure its offset with the master clock with the following mathematical equation so that they can calibrate their clock to keep it synchronized. So, of course, from the security perspective, if we just look at this vanilla version of PTP, it was not secure because it was designed about 20 years ago, and at that time there is no built-in security mechanism for this protocol. So some even very simple network level attack, such as message spoofing, manipulation, or replay, can easily actually disrupt this protocol. And luckily, there are many security mechanisms that have been proposed to address those network level attacks. So, however, little attention has been paid to the insider adversaries. Here we differentiate the insider adversaries as they are actually the legitimate node in the network. So of course, as an insider attacker, you control a node. The node you control is compromised. What we are going to investigate is about whether this compromised node can disrupt the time synchronization service for the whole network. I mean, whether they can do bad behaviors to the others. So we first demonstrate the fatal consequences caused by this insider adversary by demonstrating attack on a real hardware test bed. So we deploy a real Raspberry Pi 4 PTP test bed, and this test bed contains one server node and two client nodes. So here are some configuration details, and we assume the attacker actually controls one client node in this architecture. So the victim implementations are very famous PTP software, including the PTPD and the Linux PTP. And the attacker's goal is, of course, to shift the system time of a chosen victim node. I mean, an arbitrarily chosen victim node. We also assume that the authentication mechanism and also the previously mentioned security mechanism is in place, and we are going to investigate whether they are able to defend against our attack. So our attack can be conducted in 4 phases. So I omit some detailed cryptography here to just show the overall workflow of our attack. So the phase 1 is called the clock information extraction. The attacker obtains the current ground master clock quality information, and the second phase is priority inversion, in which the attacker will carefully craft a malicious announce message with a higher priority. And this message is also signed properly with the attacker's secret key. And for phase 3, the attacker will broadcast this crafted announce message to the whole network, and then he is trying to seize the control of the network as a ground master node. And of course, for the last phase, it's called the time shifting, in which the attacker will shift the time of an arbitrarily chosen victim, follows the two-way time transfer mechanism to avoid being detected by any intrusion detection system. So we conducted our attack on the test bed, and the result shows that the attacker successfully shifted the system time of the victim nodes in different settings. So we can find that we are able to actually add the cumulative offsets, constant offsets, and even random offsets to the targeted victim node. Or in other words, current protocol nearly allows us to do anything to the victim nodes. We also provide a case study to investigate our attack on a real robotic platform. It's called the TurtleBot 3. So our attack is able to desynchronize the sensor input and the comments to the robot. So finally, with those desynchronized inputs, the robot fails to localize itself and goes to a false trajectory. So what we can learn from this attack is like current PTP architecture that relies on a single source is quite vulnerable to the insiders. So to defend against this attack, we propose a defense mechanism, adopting the fundamental idea of using multiple servers from the very classic Byzantine fault-tolerant state machine replication literature. Unfortunately, this idea is in line with the PTP's developing trend. Actually, the newest version of the PTP has already specified using redundant servers to build up robust time synchronization service. So MS-PTP, which means multi-source PTP, is actually the defense mechanism we are proposing. So here is the network model. We assume there are not only one server, but there are n servers simultaneously existing in the network, and among them, f of them may be compromised. So we assume the honest measurements from those honest servers, denoted by D1, D2 up to Dn minus F, follows Gaussian distribution. We do not assume it is a constant value because of the unavoidable uncertainty, such as the uncertainty caused by the network conditions and the measurement method itself to measurement itself. So we also assume that the system's time synchronization requirement is R. For the threat model, we assume an insider attacker can deliver arbitrary timing measurements to their clients. So in other words, they are the Byzantine nodes. And also those insider attackers can collude with each other to conduct some attacks. So this is a very strong assumption. However, the only limitation for the adversary's capability is that they are the minority of the total population, and their number is smaller than a certain threshold. So the system goal of our mechanism is to establish a fault-tolerant time synchronization mechanism against the very powerful insider adversaries with a majority, more specifically, the two-thirds majority of the nodes are honest. And how to define the robustness? We also provide a mathematical definition of the robustness. Is like we say an aggregation rule A is robust is when its output O satisfy that the expectation of the output minus the ground truth G is smaller than bound S, and that bound is actually a non-parametric bound irrelevant to the number of the servers, and that bound is strictly smaller than the system's requirement R. Well, finally, we go to the aggregation rule itself. So we define a score like that. VI refers to the general representation of a measurement without its honesty or not. So here is what the aggregation rule looks like. It's a rather complex mathematical equation here. So for this aggregation rule, we actually provide a performance guarantee. So this guarantee is not an experiment or simulation guarantee. It is a mathematical guarantee. We are able to prove that the aggregation output O is bounded by the square root 2 times sigma max. This is the error bound of the output, and it is actually comparable to the output of honest sessions without attack. And this bound is also irrelevant to the number of the servers. That means no matter how many servers you are going to deploy in the network, you are still stick to this error bound. So we also consider analyze our defense mechanism's performance against the potential adaptive attackers. The adaptive attackers, we assume they have full knowledge of our defense mechanism, and also they conduct the following adaptive attack. So fortunately, in our experiment, we found that those adaptive attackers, they still cannot break the MS-PTP. So we conducted the evaluation part still on our test bed to evaluate the different perspectives of our mechanism. So first, we evaluated the performance of this MS-PTP by checking the accuracy and of the evaluated offset on the victim node. So we can see the result from the figure here. Without the MS-PTP, if we just use a relatively simple aggregation method, the offset of the victim node is significantly shifted by the attacker. But if we use the MS-PTP mechanism, we can see that the final aggregation result is comparable to a no attack scenario. Here, the CU, CS, and RD are different types of the attacks, different type of the attacks launched by the insider attacker. We also evaluate the communication and computation overhead introduced by this MS-PTP system. Of course, by incorporating some security mechanism, you need to have some extra overhead. So for the communication overhead, we monitored the UDP port 319 and 320 because these two ports are used by PTP to communicate with each other. And for the computation overhead, we checked MS-PTP's execution time on the PC and the Raspberry Pi. So we can see from the figure here, the MS-PTP actually introduced a linear increasing overhead to the system. with respect to the number of the servers. And considering the deployment scenario of MS-PTP that the server numbers are not that large, you cannot expect to deploy hundreds or even thousands of timing servers just in a small local network. So we expected the MS-PTP to not introduce a very large overhead to the system. We also compare MS-PTP with other aggregation mechanisms. We can find out that MS-PTP remains to be stable and was not affected by the population of the network when we increase the number of the servers. So we compare this MS-PTP with other aggregation mechanisms. Actually, these aggregation mechanisms are not customized design for the time synchronization mechanism. They are adopted from the federated learning area, but as long as they use the same logic and they are solving a similar problem, we take them here to make a comparison. And we compare them in terms of the fault-tolerant bound and the theoretical proved error bound, and also their performance when the network size becomes larger. We also validated MS-PTP's compatibility not only with the current PTP protocol, but also with the other time synchronization protocol. This is because in some scenarios, you may not have enough PTP sources to counter the malicious nodes. So you may try to get the help from some other time synchronization sources. So we considered the existence of one malicious PTP server, but with either 3 NTP honest servers or 2 NTP honest servers plus 1 GPS server. You can see from the table here, without if we do not use redundant servers, the offset of the victim node will be significantly shifted. But if we use redundant servers, no matter what kind of the server it is, we can counter this insider attacks. However, if you use NTP servers at your honest majority, you can only achieve the accuracy level in the NTP scale. If you use the GPS one, you may achieve the accuracy performance comparable to honest NTP, honest GPS server. So in conclusion, we propose this MS-PTP, a Byzantine resilient network time synchronization mechanism. So we first demonstrated through hardware experiment that the current PTP is vulnerable and to the insider time shifting attacks, in which maybe only one malicious time source is able to compromise the whole system. And to defend against this very powerful insider adversary, we designed a novel Byzantine resilient aggregation mechanism to generate an error-bounded measurement and the assumption that fewer than 1/3 of the total population are Byzantine. And we also implemented our mechanism MS-PTP on our hardware test bed and evaluated its performance in different attack settings. Okay, thank you very much for listening to the presentation. So any questions?
Okay, let's thank Shanghao and then if we have questions. Any questions? Okay, no questions for you, Shanghao. Thank you, Shanghao.